Hello and welcome to another Macron Group webinar. My name is Charles Zona, and today we are happy to welcome back Dalia Yablon. Dalia is going to talk to us today about the new capabilities in commercialized atomic force microscopy, AFM. But before we get started, I would like to give you a bit of Dalia's background. Dalia is the founder of Surface Car, an AFM consulting firm located in the Boston area. Surface Car specializes in surface and interface characterization measurements, along with education and training, focusing on scanning probe microscopy. Prior to Surface Car, Dalia spent a good portion of her career at ExxonMobil Research and Engineering, working with the chemicals division to develop new AFM-based imaging methods. She has worked in a number of cross-sector areas, including polymers, tribology, lubrication, corrosion, and unconventional gas resources, with a specific focus on developing new nanomechanical characterization methods. Dalia is also the editor of the book Scanning Probe Microscopy in Industrial Applications, published in 2013 by Wiley Publishing. Dalia will field questions from the audience immediately following today's presentation, and this webinar is being recorded and will be available on the Macron Group website under the Webinars tab. And now I will hand the program over to Dalia.
Thanks, Chuck, so much for the introduction. So today I'm going to talk about some new developments in commercialized AFM technology that have been occurring this year in 2019. It has been a very exciting year for the AFM R&D. Because this field is only 30 years old, there's still a lot of room for development of new capabilities, new hardware, new modes, and so I'm just going to review a few of them today. So I'm going to talk about three innovations that occurred in the AFM field this year. The first two are going to be new AFM modes that have come out. The first one is called AFM Nano DMA, and that's to probe nanoscale mechanical properties in the form of viscoelastic properties. It's particularly useful for soft materials like polymers and biological materials that are viscoelastic, meaning that their mechanical properties are dependent on the frequency at which they're measured. And this is really the first technique to offer an accurate and quantitative measurement at what we refer to as rheologically relevant frequencies, which is a low frequency domain of 1 to 100 hertz. The second new mode that I'm going to discuss is a narrow trench mode. This is a mode that enables the imaging of the width and depth of very narrow trenches on the order of 10 nanometers or so with specialized probes. This is particularly useful for the semiconductor industry, which needs to do these kinds of metrology measurements on that kind of level. And then finally, I'm going to talk about a new instrument that was introduced to the market. At this point, it's not so often that we get a brand new instrument, brand new platform that was designed from the bottom up. But this year we do it. There is a new entry to the market. It's called the Jupiter. It's a fast, large sample instrument with high resolution, and I'll discuss why the combination of that is not so easy to achieve. And another differentiating factor on this instrument is that it enables photothermal actuation in addition to piezo actuation, which is you really want for fluid imaging. In terms of who provides these techniques, the AFM Nano DMA is a technique that was put out by Bruker this year. The narrow trench mode was put out by Park Systems, and the new Jupiter AFM instrument was put out by Asylum Research and Oxford Instruments Company. So before we discuss measuring viscoelastic moduli on the nanoscale, let's first understand how viscoelastic moduli are measured in the bulk. First of all, what are the viscoelastic moduli, or the mechanical properties that I'm talking about? They're primarily what's called the storage modulus, which is referred to as E prime, which is a measure of the stiffness of the material. The loss modulus, which is E double prime, which is related to the dissipation in the material. And then the loss tangent, which is simply the ratio of the loss modulus over the storage modulus. And again, these are moduli that are frequency dependent, so they change as a function of how quickly you measure them. So in the bulk, we use dynamic mechanical analysis to measure the viscoelastic moduli of solid samples. This is a very common tool used in the polymer industry, where you apply a sinusoidal stress and you measure the resulting strain. Typically, the bulk DMA measurements are done as a function of either temperature over a pretty wide range or frequency also over a wide range, but notice what that range is. We're talking about 0.001 hertz to 200 hertz. This is low frequency relative to what AFM measurements do. This is an example of a DMA instrument from TA Instruments, a popular vendor. And here you can see the sample, which is in brown, and it can be held in a variety of different clamps to simulate different motions. So here it's tension, so it's going to be pulled up and down, back and forth. And then the 3-point bending is a different clamp for your material. Polymer chemists also can build what are called master curves through time temperature superposition, where you collect your viscoelastic moduli as a function of a series of temperatures or frequencies, and then you build a master curve that gives you the behavior of the moduli for that material over a very wide range. And here's just some example that again I put off of TA Instruments website. So this is showing the storage modulus in red. In blue is the loss modulus, and then the green is the loss tangent, which is the ratio of the two for a pressure-sensitive adhesive. And all these moduli are measured as a function of temperature, where this peak in the loss tangent is very instructive because in general these peaks can pinpoint thermal and structural transitions in the material. So the idea behind AFM nano DMA is now to make localized viscoelastic measurements on heterogeneous samples. And again, this was a technique that was released by Bruker this year. So the idea is the following, that you will image your sample using a standard AFM imaging technique. This is a sample with 4 different materials that have, it's a polymer blend of a cyclic olefin copolymer. This here is polypropylene. This here is polyethylene. And then this dark region here is the elastomer. And so AFM nano DMA enables you to do 2 different kinds of measurements. You can either map the whole surface at a very fast frequency, at about 100 hertz or higher. And this is giving you now a map of the modulus, either the storage modulus, the loss modulus, or the loss tangent as a function of frequency, again 100 hertz or higher. Or you can pinpoint, do point and shoot, and do very localized measurements with ramp scripting, where you sit on a particular area and then you measure the different moduli. Here we're measuring the storage modulus as a function of frequency. And here you can see we're measuring it from approximately 0.1 hertz to approximately 300 hertz on all these different materials, getting the full rheological information as a function of frequency for all these different components. So one is an imaging technique at higher frequency, and the other is a point and shoot technique where you sit on a particular area and get the full frequency dependent behavior at that localized point. You can also add temperature as a variable to these frequency sweep measurements. So here what we have is a blend of 2 materials with polypropylene in the background and a domain of cyclic olefin copolymer in the middle. And here what we're showing is the storage modulus as a function of temperature from 25 degrees to 175 degrees, and then the loss tangent from 25 degrees to 175 degrees. And we're just sitting in the same area, and now we're imaging this particular material as a function of temperature to see how these moduli change. And then we can plot, we can quantify what the moduli are on the polypropylene and the domain of the COC, and we can plot that as a function of temperature from our data, both for the storage modulus and for the loss tangent. And we can see that the storage modulus as a function of temperature for these two components diverges because a polypropylene very quickly approaches its thermal transition point. In the loss tangent, what we see is a crossover in the relative loss tangents between the two materials. So we can compare the results of AFM nano DMA with bulk DMA. There's another nanoscale DMA measurement called nano DMA, which is on a slightly larger scale, more of like hundreds of nanometers localization. That's by an instrumented nanoindenter. And so we can compare the viscoelastic measurements by all these three techniques on PDMS. And so here what we have is a plot of the storage modulus and the loss modulus on PDMS as a function of frequency. And so what we can see is if we focus on the AFM nano DMA measurements, which are in blue here, and compare them with the bulk DMA measurements that are the green line, we can see excellent agreement between the millimeter scale bulk DMA and the AFM nano DMA, which is on a length scale of about 10 nanometers. There's also some data in here from a collaborator on their own system in their lab, which are in orange, the spots in orange, and we can see that there are very consistent results across the labs and operators for these moduli. And notice that the frequency range that is covered by AFM nano DMA, which again are our blue points, it goes here from 0.1 hertz all the way up to 20 kilohertz, which is a very high frequency, but in general a very large frequency range in general with the AFM nano DMA. Again, I remind you that the bulk DMA measurement in green is a much smaller frequency range from 0.1 hertz to approximately 300 hertz. Here is some more data comparing the AFM nano DMA on a blend of linear low density polyethylene and an elastomer. And this is looking at the storage modulus. So here is the polyethylene data, here is the elastomer data, and we can see here in red is the bulk polyethylene, here in orange is the AFM nano DMA, and at the bottom here the bulk DMA for the elastomers is in light blue, and dark blue is the AFM nano DMA measurements. And you can see very good accuracy for these two different materials that are actually differing by over an order of magnitude in range in their storage modulus. And then finally, our final comparison of AFM nano DMA with bulk DMA is looking at the loss tangent of a material called a plastomer, which is a real-world example and has some complicated behavior. And so here we have the bulk DMA, and now we've looked at it as a function of temperature. So here's the AFM nano DMA. Now we're looking at the loss tangent. So loss tangent as a function of frequency. This is a bulk DMA. This is the AFM nano DMA at room temperature. And then we increase the temperature to 50 degrees C in orange and 80 degrees C in yellow. And we can see a flattening of this curve as we approach the temperature for the melting point of the plastomer, which was 92 degrees. So you can see some very complicated measurements of our viscoelastic moduli, again as a function of frequency and temperature, and that can help us elucidate important structure property relationships, especially in materials which have nanoscale features or nanoscale domains that are impossible to probe in any other way. So the second new mode that I want to talk about that was introduced this year by Park Systems, a different vendor, it's called narrow trench mode. And it was introduced this year on their automated, very large industrial systems, fully automated systems that typically go into clean rooms, but next year should be out on their research systems. And the need that this particular mode addresses is the need to be able to image very narrow but somewhat deep trenches, which are critical to metrology applications in the semiconductor industry, where they make a lot of devices with features on this order. So for example, you can see here, this is an actual sample with these trenches with the TEM image of it. And you can see the kind of aspect ratios, so depth to widths we're talking about. And this black profile is the profile of what a standard mode AFM can do, where you can see that the trenches that are especially deep and narrow, the AFM tip simply can't get in there to get an accurate measure either of the width or the depth of the trench. And so what they've done in this narrow trench mode is an interesting technique where they do what are called force curves or single point measurements, where the probe, it's not imaging, it's just coming in and out at every point. And then they've added a lateral force detection on the side-to-side motion, so that there's a very easy detection of where these sidewalls are, so that the tip knows where the sidewalls are. And these are what the probes look like. There are two different kinds of probes here that are showing data. You can see very high aspect ratio, right? So this is probe A, and that really is this, the blue, gives you the blue outline for these trenches. And you can see it not quite getting in and getting the depth or the width of these trenches. And then probe B, and these are both custom probes designed for this technique. Probe B does appear to do better. That's following the red line here. So this is a new mode that combines these custom probes with a force curve measurement and lateral force detection to be able to get a very accurate measure now on these deep and narrow trenches. And like I said, for critical device metrology in the semiconductor industry, this is really important. Okay, so to the final innovation that I'm going to discuss today. That is a brand new instrument that was newly designed and released this year. And in order to understand how this instrument fits in with other instruments, I just want to quickly go over just this one slide, that there really are two categories of AFM instrumentation when these instruments are designed and built. There are what we refer to as a small sample instrument, where the sample is what is moved and scanned under the tip. And this is really the kind of instrument you want to do for the high resolution work, like atomic scale work. The problem is that it comes with a very limited sample size, and that's because if the sample is being moved under the tip, and imagine these samples are being moved tiny amounts, 15, 20 nanometers, you can't have a large mass being moved around. So the sample size is limited, and typically they're limited to about samples that are 15 millimeters in diameter and only a few millimeters thick. For many samples it's great and things can be cut down to that size, but for many samples it's not. So there's a different design, a different approach to building AFM equipment, which is called the large sample instrument, where now your sample is stationary and the tip is what is scanned over the sample. So every design has its pros and cons. The cons of a large sample instrument is that typically it will struggle with higher resolution work because the motion and detection is being done by the tip. Whereas here the motion is being done by the sample and the detection being done by the tip enables better signal to noise ratios on a small sample instrument. Here the tip is doing all the work, so it can compromise high resolution measurements. It can also struggle with high-speed measurements because the samples can be very big. One of the biggest pros of a large sample instrument, obviously by its name, is that it can handle large sample sizes. And this has historically been driven by the needs of the semiconductor industry, where they have wafers now that are a couple hundred millimeters in diameter, so clearly will not fit into this kind of measurements for the kind of critical device measurements that I just mentioned previously with the narrow trench mode. So the need for instruments that can handle larger sizes has been driven by semiconductor industry, but it's benefited so many other industries. One of the examples I like to give is when I was at ExxonMobil, one project I had to do was look for very thin lubricant films, but on engine parts. And those engine parts we threw into a large sample instrument, and we were able to measure them. There's no way we would have been able to work on them if we had just small sample instruments. And many vendors offer both designs. They have a small sample instrument version and a large sample instrument model. So again, pros and cons of different ones. And what the new system that has come out is a new entry into the large sample instrument category. So here is the new instrument that was released this year. It's called the Jupiter AFM by Asylum Research, which is an Oxford Instruments company. And here you can see a picture of the actual instrument. So the instrument's in here, and you've got some vibration isolation and controller down here. So really it's a standalone instrument. And here are the pertinent specs of this new large sample instrument. So in Z, it's got a 12 micron range, which is quite large. A lot of instruments usually only go up to 5 microns. Here's our large sample component, the chuck, which you can see here. This large circular portion here. It's a 210 millimeter sample chuck, and it can accommodate samples up to 35 millimeters in height. So a lot of flexibility there. Where the sample chuck is motorized and fully addressable. And the XY scanner is kind of a classic 100 micron range in X and Y, classic for most of these large sample instruments. It combines a couple of key and very helpful features. One is an automated laser alignment, which is a step in running AFMs that a lot of users struggle with. And they've integrated point and click alignment of the laser onto this cantilever here. It's a similar point and click alignment that they have on their small sample instruments also, but it makes a laser alignment fairly trivial, so that's good. And then another feature that they've integrated into this large sample instrument is how we drive the cantilever. So driving the cantilever, meaning that we shake it so that it's oscillating, typically at a resonance frequency, so that we can image in modes called tapping mode, for example. Typically the way we do that is we have a piezo underneath this cantilever, and it will shake, and thereby shaking the cantilever. And that is piezo actuation is what we've all been doing for 30 years. And this technique is called it's a different drive, by using now a blue laser here that is going to drive the cantilever instead of that piezo. And the advantages of that is you get much cleaner tunes, much cleaner tuning curves. So for example, here is a tuning curve for a cantilever with a resonance at 1.14 megahertz, and you can see how there's no shoulders, there's no noise. It's a very clean way to drive the cantilever, and this has really become very game-changing in working in fluids. To be able to drive your cantilever with this photothermal excitation as opposed to just piezo excitation is a huge step forward for fluid imaging, because in fluid imaging it's actually very difficult to get good signal to noise on your tunes because of the damping of the cantilever by your fluid medium. So for people doing fluid imaging with large samples, this is going to be a very useful addition. And so here are just some examples of applications of now taking advantage of this large sample instrument to do very high resolution imaging. So here was data that they collected from the edge of a razor blade. So you can see here's the edge of a razor blade, obviously an irregularly shaped sample, didn't have to be cut up. The razor blade's actually sloped. It's got a sloped edge. And the reason that matters is, so if we can see here, the slope of that edge actually is about 9 microns. In a small sample instrument that has a Z range of only 5 microns, you would not be able to image that whole slope because you'd run out of Z range. But having this large sample instrument with the large Z range as part of it enables you to measure this entire range. And so not only do you get the full range, but now you can get a very high resolution image of the structure and morphology on this razor blade as shown here. This is our AFM topography image, and they can overlay that even onto the optical, so you can get a nice compare and contrast that way. Here is an example of taking advantage of the ability to image in fluid with this photothermal actuation and combine it with high speeds, which you typically don't see on these large sample instruments. So this was collagen, which was deposited on mica and imaged in a buffer solution. You can see these collagen fibers very clearly. And this is actually a high resolution image of only about 300 nanometers on a side, where you can really see the fibrils in the collagen fiber here. And you can see it was actually scanned pretty quickly in fluid at 10 hertz. Typical scan rate for AFM images is on the order of 1 to 2 hertz. So this is pretty fast, especially for a large sample instrument, and getting really crisp, clean resolution in fluid. And I just want to end with a couple of slides showing the high resolution that this large sample instrument can achieve. And if you remember from one of my earlier slides, one of the drawbacks of a large sample instrument is the ability to get high resolution because that all the work and the detection and the motion is being done by the tip, so it can be very noisy. And here's a nice example demonstrating on a silicon wafer, very smooth silicon wafer. So notice what our Z-scale and height here is. It's only 1 nanometer. And they've moved to different points on the wafer from the very edge, now down all the way to the middle, which can be done now, even though this is a large 210 millimeter wafer. You can see the structures changing at the wafer center versus edge with these very fine Z resolution, being able to pick up only a few angstroms in height change all across the surface. And then finally, this example of a self-assembled monolayer of this long chain hydrocarbon. It's called cetyl palmitate. And it self-assembles onto a highly ordered pyrolytic graphite surface. And so this is a height image, and this is a phase image in tapping mode. And what you're seeing is a self-assembly of single molecules here, where these features are spaced apart. These features, the lamella in these molecules, only by 4.3 nanometers. Their height is 100 picometers. And you can resolve it also in the phase image. So very impressive resolution that you would expect to see in your small sample instruments, but now you can see in this large sample instrument very clearly. So this concludes the 3 innovations that have come out this year that I wanted to review. The 2 new modes were the AFM Nano DMA and then the narrow trench mode, and then the new instrument is the new large sample instrument, which is the Jupiter. And next time, I'm also going to talk about a fairly new area in AFM. The next webinar will be on machine learning in AFM and how can we use machine learning to improve image analysis and experimentation with AFM. Seems like machine learning is everywhere these days, and we've been working on trying to understand how it can improve AFM. And here's just an example of a neural net that one might construct to look at the different parameters coming out of an AFM image on cells and trying to then interpret or assign, classify whether these cells are benign or malignant. So that will be the next webinar, still working in the area of innovations coming in AFM. Thank you so much for your attention, and I'll be happy to take some questions.
Okay, thank you again for attending today's webinar. If you have any questions, please go ahead and type them into the questions field. And during the presentation, we had one question come in from Bill. He says, for AFM and DMA, why does it matter if you measure the properties at rheologically relevant frequencies?
Yeah, that's a really good question, Chuck. So when I talked about rheologically relevant frequencies, what I mean is a low frequency range from on the order of a hertz to 200 or 300 hertz. The reason we call that rheologically relevant frequencies is because bulk measurements like DMA or other rheological measurements are always done in this frequency regime. The reason this was an innovation in AFM Nano DMA is that pretty much all other AFM techniques conduct measurements at much higher frequencies in the kilohertz or even megahertz region. And for materials that are viscoelastic, i.e. their properties depend on the frequency at which you conduct the measurement, the AFM measurements in kilohertz and megahertz were, I would say, not as useful because it's much more difficult to compare those kinds of measurements to the bulk low-frequency measurements, because obviously a modulus measured in the kilohertz regime is very different than the modulus measured in the let's say 10 hertz regime. And so that's why conducting measurements in a more rheologically relevant frequency range, again in the range of 1 to 2 or 300 hertz, is really important for any comparison and validation to other techniques, all of which operate in this low frequency regime.
We have another question from Paige. Does the Jupiter AFM enable the largest sample scanning on the market?
Right. So the Jupiter is not setting any records for how large a sample it can image. There are a couple of other commercial instruments out there that also can image and work on large samples on the order of 200 millimeters. What the Jupiter did represent was the entry into the market for asylum research into being able to handle these large samples. And then they have integrated a couple of other new features with the large sample that are new, like the photothermal actuation that I had mentioned, and an automated alignment for any scan size that you want to do. But in terms of the pure size of the sample, it is consistent with the other largest samples out there that can be imaged with AFM.
All right, here's a question from Mason. Are any calibrations required for AFM NDMA?
Yeah, so calibrations for nanomechanical measurements with AFM are always a concern. The short answer to this question for AFM nano DMA is there are calibrations required, but they don't have to do with the actual mechanical measurement per se. So for example, you need the spring constant and deflection sensitivity, which we always need for any of these measurements. And you can do them either in the traditional way, which is a thermal method, or you can now buy cantilevers that are pre-calibrated by laser Doppler vibrometry, and then the sensitivity, the optical sensitivity calibration is done the way it's always been done, which is a force curve on a stiff sample like sapphire. But the technique doesn't require any tip shape calibrations, which is always the concern for these nanomechanical measurements. In addition to the spring constant and sensitivity measurement, it does have another calibration required, which is related to the electronics and the phase of the instrument that you have to calibrate also on a sapphire sample. So that is a step that has to be done, but the classic kind of tip shape and tip radius calibrations are not required for AFM nano DMA.
All right, that will do it for the questions. I'd like to thank Dalia for another great webinar, and to all of you out there that tuned in today. I also want to mention Dalia's upcoming AFM course that'll be held in April at our facility here in Westmont, Illinois. And for more information about the AFM course that's taught by Dalia, you could check out our website. And just want to wrap up by saying have a great day, and we hope to see you at a future Macron Group webinar. Thanks.